Back in 1982, the Commodore 64 debuted with best-in-class capabilities thanks to a set of custom chips. Over time, those chips have started to fail, but the enthusiast community has responded by designing replacements. For years, we've been able to purchase new CPUs, PLAs, and SIDs, but no such alternative existed for the VIC-II. That is, until now. The video interface chip is one of the most important custom ICs in the Commodore 64. If your original failed, you'd have to try your luck with a used part that was pulled from another machine. That all changed recently with the introduction of the VIC-II Kawari.
Kawari, which is Japanese for instead, is the brainchild of Randy Rossi. You may recognize the name as he's also the creator of the bare metal BMC64 emulator. His latest project is a drop-in replacement for the VIC-II video interface chip found in the Commodore 64 home computer. At the heart of the Kawari is an open-source FPGA core written in Verilog. Such field-programmable gate arrays can be configured to mimic the original hardware, performing all of the same functions of the VIC-II chip. This includes not just video output, but also the generation of timing signals for DRAM refresh and the CPU's Phi-2 clock, as well as things like handling light pen interrupts. Big projects like this don't happen overnight, and the Kawari is no exception. The first demonstration of a working concept was revealed to the world all the way back in June of 2020. At that time, a few other FPGA-based projects already existed, but they were part of complete system implementations like the Ultimate 64 or unfinished prototypes. Because no functional standalone core existed, Randy started to build his replacement VIC-II from scratch, using breadboards and a development FPGA. In order to validate his core, Randy developed a bridge between the Vice emulator's VIC-II implementation and his own Verilog simulation. This would prove to be an invaluable tool throughout the design process, allowing him to quickly verify that the FPGA core was able to produce a pixel-perfect reproduction of the emulator's output, given the same set of inputs. At this stage, it was limited to only text and approximate color, but the project soon reached a point where it was ready to be connected up to a real 64. Upon doing so, the machine would boot and respond to commands, but would only display a black screen. This meant the CPU was running and the Kawari's DRAM refresh was working, so good news there. A significant amount of time was spent troubleshooting and debugging data bus and timing issues, but progress was steady and new capabilities were being added, including sprites, collision detection, and support for the glitches and exploits used by demo coders. One by one, the warning messages in the Vice bridge were being resolved, until finally none remained. It was at this point that Randy wondered if there would even be any interest in the product. Spoiler alert, I think we all know the answer. Of course, retrospect is 2020, and at the time, his concern was that it might not be economically viable. By December of 2020, the prototype had gone as far as it could with the limitations of breadboard development. Signal noise was starting to become a real issue, and it was preventing the project from moving forward. In an attempt to mitigate the problem, Randy designed and had fabricated a proper printed circuit board. Unlike the compact versions that were to come later, this initial effort was built to mate with the Spartan 6 development FPGA board. Too big to fit inside a C64 case maybe, but still a huge step forward from the breadboard spaghetti. By now, the requisite base functionality was nearing completion. Additional testing was done to verify that all the VIC-II regression tests in Vice were rendering accurately on the FPGA core. Of 280 tests, 279 were working, with only one exhibiting a minor discrepancy. There were also occasional random crashes, and the signal noise issue from earlier hadn't yet been completely eliminated. Now February 2021, an updated PCB was built and all of the crashes were resolved. As it turns out, it was the piezoelectric speaker on Randy's Pi 1541 that was responsible for causing the signal noise issues. Extended capabilities were now being added to the FPGA core, taking it beyond the original VIC-II design. New registers allowed for the use of additional video RAM, which in turn enabled all new graphics modes. The system palette could be selected from 4,096 possible colors. Switching between NTSC and PAL was implemented, and a hardware 80 column mode was added. A few months later, in May of 2021, a new single-board PCB design had been completed, reducing the cost, complexity, and size. The latest iteration also supported composite and split lumichroma output without the need for a separate, dedicated encoder chip by using the FPGA itself to generate the signals. It was at this point that the single design began to diverge into several permutations, each with a different PCB layout, feature set, and associated cost. Hardware acceleration was added to the 80-column mode to increase rendering performance. 4 months later, in September, all of the primary and secondary goals for the project had been met, and it was time for a beta test. A pre-order opened up for the first batch of devices with a delivery target of January 2022. Of course, we all know what happens to the best laid plans in the time of COVID. A familiar story played out as setbacks due to chip shortages delayed everything. January came and went, and by July, component prices had jumped tenfold, with a 2 to 3 year backlog on some parts. This necessitated a redesign from the existing Spartan 6 to a totally different Tryon FPGA, and just as the new dev boards were completed, the supply of those chips dried up as well. This hastened the bifurcation of the Kawari into different models per the earlier plan. Randy had enough parts on hand to build 7 large boards using the Spartan 6 and 44 mini boards using the new Tryon FPGA. He also added a DMA transfer capability to allow fast data copy from main memory to video RAM, rudimentary math coprocessing functions, and blitter. Fast forward to October of 2022, and a website was open to the public in order to sell the Kawari in small batches as they became available. As of July 2023, around 700 units have been sold in total. I guess that answers the question about whether there was interest in the project or not. I purchased a Kawari Mini from the most recent batch for the listed price of $77 US. That may seem like a lot when an entire 64 can be had for around $100, but is it really? Setting aside all the awesome new features, let's take a peek at the going rate for a used VIC-II these days. Here are a few examples of chips that have been sold recently on eBay. As original parts fail, tested working replacements are getting more and more expensive. With the earliest examples now over 40 years old, there's no telling how long a used replacement will last before it also dies. For that reason alone, it's awesome that we finally have a viable modern alternative. I hope you now have a better appreciation for the amount of hard work and dedication that went into bringing this concept to reality. That was just a short summary of the development process from Randy's own YouTube blog. If you're interested in more detail, a link to his channel is in the description. Now, let's unbox, install, and test out the new VIC-II Kawari. The plan is to install this new video chip in my Evo 64. Inside is a modern, high-quality replica longboard with dual SIDs, which the Kawari will complement perfectly. Included in the box are some basic installation instructions, along with the Kawari Mini itself, the board being dominated by the large FPGA chip in the center. The Mini version doesn't offer RGB or digital output like its big brother, providing only composite and split lumichroma, just like an original 64. I already have a Mr. FPGA and an Ultimate 64 for times when RGB or HDMI is required, but I want to keep the Evo true to the original experience and plan to use it with period-correct CRT monitors. Before we install the device, we need to set a few jumpers. The first block configures the use of the Kawari's onboard oscillator to provide both NTSC and PAL clocks. This must be enabled if you want to use both of the video standards. It's also possible to use your 64's original crystal, but that will limit you to your machine's native region. The second set of jumpers configures the device's behavior. F prevents software from flashing the Kawari's firmware, a precaution against malware. E allows you to disable all of the extended features such that the device will only behave as an original VIC chip. S disables overwriting of stored preference settings. The defaults are already good, so there's no need to change anything unless we want to update the firmware later on. So, why choose the Evo 64 to upgrade? There are several reasons. First, the board is already capable of running both PAL and NTSC VIC-IIs, and it also supports dual SIDs, so it's been my go-to machine for playing games, music, and demos regardless of region. The Kawari will make it even better because I'll no longer need to swap VIC chips or jumpers around. I've been borrowing parts from my PAL 64C, so it'll be nice to put them back where they belong. The Evo has jumpers for VIC voltage as it supports both old and new style chips, but the setting doesn't matter here. The Kawari only draws from the 5V rail and ignores the 12V pin entirely. The board has crystal oscillators for both NTSC and PAL, but we're using the Kawaris now, so once again, the setting can be ignored. When installing in an original 64, it may be necessary to remove or trim parts of the RF shield surrounding the VIC, especially when using the large Kawari. On the Evo, the Mini just drops right into place. One thing to note is that the product ships with an extra dip socket already installed to give the board the clearance it needs when used in a regular bread bin. Clearance below isn't an issue on the Evo, but the Kawari will interfere with the keyboard in the 64C case if the socket is left in place. It's kind of hard to see, but there's just enough space for the Kawari under the keyboard once the extra socket is removed. It's also a perfect fit with the NewTube 64 preamp module. If I didn't know better, I'd say they were designed this way, but I'm guessing it's really just a happy coincidence. The Kawari has been tested with the following models of Longboard 64. The device is also partially, but not fully compatible with the later 64C shortboards due to clearance issues and slight differences in memory timing. It also won't work in the Commodore 128, which uses a special VIC-II with 8 additional pins for the Z80 clock, numeric keypad, extra keys, and 2 MHz toggle. The large version has been tested to fit the same longboard models as the Mini, but you may need to cut or remove the VIC's RF shield if you want to run an HDMI cable. It's also recommended that you remove the RF modulator or install a bypass to allow the cable to exit the back of the machine through an existing hole. Right out of the box, the Kawari works just as you'd expect. Let me load up the supplied configuration program because I want to show you what I consider to be the single best reason you might want to consider one for yourself. That reason is the Kawari's ability to effortlessly switch between the NTSC and PAL video standards. Doing this is as simple as selecting which VIC-II model you want the FPGA to replicate and power cycling the machine. Alternatively, you can wire up a physical switch to a header on the board. Of course, you will need a display or upscaler that can support both standards in order to take advantage of this capability. The Kawari can replicate 4 models of VIC-II chip. The 6567R8 is the penultimate NTSC revision from Longboard 64 sold in North America and Japan, while the 6569R3 is from PAL models sold in Europe, Australia, and parts of South America. 2 earlier variants have also been provided, giving users of older 64s an authentic experience if they so choose. The R56A is the earliest NTSC revision, and the R1 is the earliest PAL variant. Be warned, the Kawari replicates the bugs, non-standard horizontal frequencies, and fewer luminance levels that these earlier chips were known for. Here's the Kawari outputting NTSC and connected to my Commodore 1084S. A quick switch program is provided if you just want to change video standards. When I select a PAL model and restart, the monitor is able to sync to the 50 Hz horizontal refresh, but it can't decode the color signal, so we only see a black and white image. To use PAL here in NTSC land, you'll need a display that supports it. Or will you? If we hop back into the config utility, we'll find an option there called NTSC 50. If we enable this, the Kawari continues to use PAL resolution and timing, but outputs an NTSC color signal that our monitor can decode. With this, we can run PAL software on NTSC displays, provided of course they can handle the 50 Hz horizontal refresh instead of the usual 60. This is a killer feature never before seen on the 64, and it's a total game changer. Now, if you don't have a CRT capable of NTSC, PAL, or PAL 50, fear not. Many modern LCD screens still have composite or S-video inputs, and a lot of them can decode both video standards because the same models are sold in more than one market. If nothing else works for you, you can always invest in an upscaler that can handle both signals. You may be wondering where the PAL 60 mode is, and it was added to earlier experimental builds, but it isn't included in the release firmware due to some problems with a distorted picture in color. Okay, so that's great and all, but why would you even want to use a video standard other than what your 64 originally had? In short, because not all software runs correctly, or even at all, when used on a machine from a different region. Take the Nuvie video player for example. The playback logic relies on timing specific to 50 Hz machines, so it's completely unusable on NTSC hardware. With the Kawari, however, that's not a problem. We just switch to PAL, and everything works as designed. The same is true in reverse as well. Take the stereo SID player for Compute's music system, something I covered in depth way back in episode 55. The program itself seems to run on a PAL machine, but none of the notes are played back. This time, the software must rely on timing that's locked to 60 Hz instead. Switching the Kawari back to NTSC allows us to enjoy these early tunes that were popular in North America around the time of Quantum Link and dial-up BBSs. Across the Atlantic, .SID files were instead the norm, and these were generally composed using 50 Hz systems. While they still can be played on NTSC hardware, the tempo is far too fast. Switching once again to PAL lets us hear the compositions the way they were intended. Since we're here anyway, let's take a moment to appreciate the Evo's dual SIDs, NewTube 64 preamp, and how the Kawari really is the perfect upgrade for this machine. These cross-compatibility problems also plague the Demoscene as well. The vast majority of productions come out of Europe and are often horribly broken or simply don't run at all in NTSC systems, leaving a large swath of owners unable to enjoy some of the best content the 64 scene has to offer. With the Kawari installed, however, this problem has now become a relic of the past. Maybe you're not into demos, but perhaps you like to check out the occasional game instead. Here's one, running in PAL the way the developer intended. While this one is pretty difficult as it is, let's see what happens when it's played on an NTSC machine. Once again, the opposite holds true, and many game titles were developed for NTSC machines, such as Kung Fu Master here. At 50 Hz, the experience is subpar. All of these issues that arise from the different video standards and timing have plagued the Commodore community since the earliest days, and apart from emulation, there's never been a great way to deal with it. The Kawari changes all of that, which is why I said earlier that I consider this to be the single best reason you might want to consider one. Now let's take a look at some of the other capabilities, starting with true hardware-based 80-column text. In the past, there have been software solutions that used half-cell bitmap graphics to simulate this mode, and it worked, with a few compromises. This is the real deal though, and it's even possible to switch back and forth between the 40 and 80-column text modes seamlessly. A small utility is provided that patches the basic screen editor with support for the increased width, and everything just works exactly as expected. In addition to the basic shim, a new driver has been provided for the popular NovaTerm and StrikeTerm software, allowing the use of hardware 80-column mode when going online. The driver uses the hardware's blitter capability to accelerate copy and fill, so scrolling text is extremely fast. Here, the text speed is only limited by the baud rate of the modem. NovaTerm has featured a software 80-column driver since the late 1980s, and it worked okay when paired with a good monitor. Due to how each 8x8 pixel graphic cell is split into two 4x8 pixel text characters and the 64's palette limitations, it's not possible to accurately reproduce the color of adjoining symbols, which results in a slightly corrupted image. With the Kawari's hardware driver, each text character can have its own unique foreground and background color, so the ANSI artwork renders more accurately. I've also loaded a custom palette so the colors align with the IBM standard. The 64 still can't reproduce all of the symbols from the PC character set, for that you need a 128, but this new mode closes the gap quite a bit. To get the most benefit from this new mode, you'll need a high quality display. Let's see how it looks on a few different period correct CRTs, starting with this 13-inch Sony PVM. It has 600 total video lines, a 0.25mm dot pitch, and is connected with an S-video cable. Now, let's try it on the Commodore 1084 using a standard split Luma chroma cable. This is also a 13-inch viewable display with 600 lines of resolution, but unlike the Sony, it uses a slot mask with a 0.42mm dot pitch. Despite that, 80-column text still looks excellent on this display, as does everything else that puts out a 240p video signal. Finally, to drive the point home, here's the same text on the Sears Total Video system. I don't have concrete specs, but this 13-inch shadow mask CRT likely uses a commodity television tube with around half the total number of video lines as the monitors we just looked at. We can only connect the 64 to it with composite as seen here, or... This really serves to highlight the difference between a monitor and a TV. And if you think that's bad, here's what the software 80-column driver looks like. Hard to believe, but some of us were actually using this back in the day. I mentioned this before, but the Kawari's color palette is user-definable. That opens up a ton of new possibilities for developers, like how we saw the IBM CGA colors being used to properly display ANSI graphics. Another possibility is real-time palette swapping techniques, which were used by many games and animations of the era. A tool is provided so you can tweak the colors as you like. The default PAL and NTSC palettes were replicated from original VIC-II hardware using scopes to measure and reproduce each color's parameters. You can thank Adrian from Adrian's Digital Basement and Mark from the Retro channel for the accurate color reproduction. Another use of custom palettes is for displaying images using the new 320x200 graphics mode. In this mode, each pixel can be set to any of the 16 defined colors, a big step up from the VIC-II's limit of 2 colors per 8x8 cell at this resolution. The Kawari also implements a new 640x200 graphics mode with 4 colors per pixel. In order to support these new modes, an additional 64K of video RAM was provisioned, enough to allow for double buffering even when using this new, higher resolution. Another feature that could be useful to developers is the ability to arbitrarily split high and low-res screen modes. This small demo shows off the new capability by using raster interrupts to alter the screen split in real time. The new blitter function allows blocks of memory to be copied around quickly without tying up the CPU, similar to the Amiga's Agnes chip. In this example, the objects being moved around are not sprites, but rather high-res bitmaps. Finally, math coprocessing for high-speed multiply and divide operations was added. With all these new capabilities, it'll be interesting to see if the game and demo coders choose to add them to their toolboxes or not. Purists may argue that it's no longer a C64, but personally, I love witnessing the continued evolution of the platform, now 40+ years after its debut. Before wrapping this thing up, we should probably talk about some of the Kawari's limitations. As with all new hardware, there have been a few teething issues as development progressed. Be aware that some TVs and monitors may not work correctly with the non-standard resolutions and refresh rates of the large board's digital video output. Depending on your HDMI display, it may not be possible to achieve an accurate 4:3 aspect ratio. Further, the digital output will make your C64 look pixel perfect, just like an emulator. When using the Kawari's onboard clock, some expansion cartridges may not work correctly, including the Super CPU, RAM expansion units, Link 232, and Turbo Chameleon. I found that my 1541 Ultimate 2 Plus worked fine, but needed the latest firmware update. For the others, it's possible to perform a wire mod to bring your Kawari's dot clock to the cartridge port. Alternatively, you could just flip the jumper and use your 64's original crystal and video standard when using these cartridges. So what does the future hold for the Kawari? The Verilog code is now open source, so hopefully we'll start to see new development and capabilities from the enthusiast community. The PCB design files will be released as open hardware within the next few months as well. It'd be nice to see the price come down as supply shortages ease and the product starts to become available through third parties. I'm also really excited to see what kinds of new utilities, games, and demos will be created in the coming months and years that take advantage of all the cool new features.
I've said it before, and I'll say it again. We're truly living in a golden age of the C64, and we're very lucky to have people like Randy creating new products like the VIC-II Kawari to keep our old and new machines running. With this, we're one step closer to having replacements for every single custom MOS chip. Actually, with the new JCIA 64, we're already there. I hope you enjoyed this bit. Thank you so much for watching, and we'll see you next time on Retro Bits.